Welcome to the next video in our series on Chapter 5 material, which is, in this case, a short video just on assigning E and Z nomenclature of carbon-carbon double bonds. So we just want to kind of add this little video to this material to just kind of cover this topic very quickly. And so we'll take a look. I've already drawn a couple of double bond containing molecules here. We've got two different molecules here. We call these geometric isomers. So we call these geometric isomers because they vary only about the geometry around the carbon-carbon double bond. And if we think back to our model of that double bond with that two bonds between two carbon atoms, that molecular orbital, strong overlap, these molecules are not interchangeable between each other. You'd have to break that double bond and then rotate around to get to the other isomer. So these are distinct molecules with respect to each other. And so what we need to be able to do, at least from a nomenclature point of view, and we'll talk a little bit more about the chemistry of these double bonds when we get to Chapter 7 material in a couple of weeks, but here what we want to do just strictly from a nomenclature point of view then is to be able to describe to another competent chemist which one of these two isomers it is that we're describing. And so we want to develop a nomenclature method to be able to describe that. So we'll look at each of these in turn and just kind of talk a little bit about the nomenclature of this. We'll look at a very quick example and we'll kind of move on from there. So here we have and of course what I haven't drawn in explicitly in the previous structure, but I'll put it in here, is the hydrogen atoms that are on that double bond as well. Of course we know that they're there. And in this case, what we're looking at are the highest priority substituents, and we'll talk in a minute about how to assign that priority. We've already done some of this when assigning R and S priority, and it follows the same rules. So the highest priority substituent is in this case, on the opposite side of the double bond, and so we use the designator E for that. That comes from the German word Entgegen, which is translated into opposite. So here the double bonds are, the substituents are on opposite sides of the double bond. That gives us the E designation, and the full name of this particular molecule then would be E2 butene. So it's a way of it's a nomenclature device that we have to be able to describe to another competent chemist which one of the two possible geometric isomers that we're looking at around that double bond. Okay, so let's look at the other geometric isomer and the nomenclature associated with it. And again, here we had both of the substituents. In this case, of course, the methyl groups are the highest priority substituents. And we'll do just a couple of brief examples of this in a minute. So those two substituents, those two methyl groups, are on the same side of that double bond. This is given the designator Z, letter Z, from the German Zusammen, which is roughly translated into the word together. And so this, again, this particular molecule is both of the substituents are on the same side or together on the same side of the double bond. So this molecule will be given the designator, excuse me, Z2 butene. I'll be given the designator Z2 butene on the same side of that double bond. Now, I'll just make a comment on other nomenclature that we may have used to hear associated with this. So you would have at one time heard us use these phrases a lot. Our textbook still uses these phrases a lot, where we would have described this as a trans or cis double bond. And of course, the trans names means across to a certain extent. Cis is on the same side. So we would have talked about cis and trans double bonds, but those phrases are really a bit obsolete, and we really typically don't use them for double bonds anymore, simply because they're a bit confusing once you get past anything that's a disubstituted double bond. So it's just safest not to use them at all. Now, that said, they're still somewhat commonly used. You might even catch me the odd time sort of saying cis and trans without thinking, because they were such a common use for a long time. But we try and discourage the use of those to describe double bonds and stick with E and Z to be able to describe those double bonds. So let's do a couple of examples of just assigning priority for E and Z double bonds, and the rules for assigning priority are identical. They are the rules that we also use for assigning E and Z for RNS nomenclature. Just in this instance, we're looking at things that are on the same or opposite side of a double bond. So here, for example, I'll draw this molecule OCH3. So here's just an example molecule, and all we want to do is to assign whether the configuration at this double bond is E or Z. And so what we look at is the priority order of substituents on each side of the double bond. So for example, we imagine drawing a line down the center here, and then assigning the priority of the substituents that are on either side of that center line. So here, for example, on the right side of the molecule, of course, the hydrogen atom is the lowest priority element on the periodic table. That's going to be 2, and this will be 1 here. So the OCH3, because it's got the higher atomic number, is the higher priority substituent than the hydrogen atom with the lowest atomic number. And then on the other side of that dividing line that we've drawn down the center of our double bond, we do the same exercise. That aromatic benzene ring, that would be priority substituent 1. That's the highest priority substituent. It's got a carbon atom attached directly to the double bond, and that carbon atom's got other carbon atoms attached to it directly, whereas that ethyl group would be priority substituent 2 in this particular example. Okay, all of the rules of assigning priority are the rules that we use for RNS nomenclature, which we covered quite a bit in that video, and we've seen some examples in class of that. So now, all we have to decide is whether this is E or Z. And so here in this instance, the highest priority substituents are on opposite sides of the double bond. The highest priority substituents are on opposite sides of the double bond. This would be an E configuration that we would assign to that. And again, this is just purely a nomenclature thing. It's not an observed thing. It's just a nomenclature thing that we've invented as chemists to be able to describe the configuration about that double bond. Okay, we'll take a look at another example here just to kind of set these priority rules in our mind. So we've got, again, another double bond. And all we want to do is use the same priority rules that we established for RNS configuration to decide whether the highest priority substituents, in this case, are on the same or opposite sides of the double bond. And so on the right-hand side of this particular molecule, I think it's quite straightforward for us to make that assignment. The bromine is the highest priority. The hydrogen is the lower than bromine, so that's going to be number 2. And again, we're looking on either side of that center line that we've drawn down that double bond. So just to be able to decide which substituent is priority. And now on the left-hand side of this particular double bond, on the left-hand side of that red line, we want to be able to take a look at, and we just try and decide which substituent's got the highest priority. As we come out from the bottom, here we see a CH2 group with then in turn is attached to a cyclohexane ring. So all carbon atoms and hydrogen atoms on that side, whereas that top substituent has got a CH2 group which is in turn attached to the higher atomic number oxygen, so that whole substituent beats the whole cyclohexane ring on the other side. So that's priority substituent number 1 with the OH group on it, that high atomic number oxygen. And down on the bottom, that's priority substituent number 2. And then assigning E and Z is just a matter of whether the highest priority substituents are on the same or on different sides of that double bond. In this case, they're on the same side of that double bond. And so if they're on the same side, that makes a Z priority substituent on that double bond. And I'd say if you're having a little bit of trouble kind of following this along and you're still not really sure, there's a number of really good examples in the problem section of the textbook to be able to get some more practice on doing these. But for now, we're going to leave it on this video right here.